Hey people! Alright, let's take up this question. Hopefully you guys got a chance to, try this one out. Now, this one is going to be tricky. Okay? It's going to be tricky. The question is this. HCl. When that breaks to become H plus and Cl minus, does it matter if H just comes over here or comes over here? Because if you look at the rich gets richer in this case, nobody's rich here. This carbon is not hooked up to any H's. This carbon is not hooked up to any H's. So where would this H go? Or does it matter where it goes? Now, if you think about it, this bond will still break. Okay? This bond will still break. The electron can come over here or it can come over there. Okay, so this guy have the potential to become negative. This guy can have the potential to become negative. But the question is, who becomes negative? Okay. Now, it really doesn't matter in this case. It really doesn't matter. Even though this molecule is not symmetrical, it's really not. Its size is a lot longer than this side. Think of it as like this way. Okay, so let's say in this situation, we have this, where this is negative. Okay, and we have this situation. Where this is negative. Okay, think of this guy. Okay, think of this carbon and think of this carbon. Think of this carbon first. He's a very negative carbon. So negative that he's being hovered around also by a lot of electrons. He's going to be angry, is he? Okay? But at the same time, look at this carbon. I know there's a lot of electrons here, but there's also a lot of electrons here. This guy doesn't mind being here. He really doesn't. It's very negative here. Very negative here. Okay? I can stay. I can. But take a look at this situation too. Same idea. Take a look at this carbon. Oh, so many electrons. So many electrons. Well, I'm positive. I'm okay. How about my friend over here who's negative? Oh, so many electrons. So many electrons. I feel very uncomfortable being here because I'm also very negative. Can you see that both situations are really the same thing? Okay. Both situation is pretty much identical. It really doesn't matter. Well, you may be saying, well, isn't this situation a lot worse? Because when it comes to negativity, the amount of negativity here and the amount of negativity here is more than this situation where this negativity is less. Hey, but look, this negativity is more. It's the same thing. So what does that mean? That means, let me get rid of this water here. We'll come back to that. Both of these will exist. Okay, H right here can attack this carbon or that carbon. It doesn't matter. So what we are having here is that we're going to have initially two separate compounds. We're going to have this and we're going to have this. Okay, they will both exist and they'll both be there. Now, this is the fun part. Because remember, this reaction continued with water being added. Now does it matter? Now, do Markovnikov rule play? Well, your answer better be yeah. Markovnikov rule do play. Because when this bond breaks, okay, this carbon and this carbon has money. and money will go where money is. So this will be your product. This will be your other product. Okay, so for this pretty cool reaction here, and a pretty cool example, you'll have two products being formed. Okay, because for the first reaction, Markovnikov rule actually don't apply. Okay, but for the second reaction with the water, Markovnikov rule do apply. Okay. So if you got that, pat yourself on the back, not too hard. You are going to be okay because you are thinking outside the box. You are thinking scenarios, because that's what organic reaction is really all about. You know, looking to see if there are multiple scenarios, just like today's lesson on benzene, reaction of aromatics. So let's very quickly take a look at another reaction. Okay, so reaction of benzene, because lots of situation here by play. Okay, there'll be three reactions. So let's take a look at the first one. I have a benzene. Okay, now what you need to remember is that for benzene, each carbon is connected to one hydrogen. We hardly illustrates that, but you get to know that it's there. If I react this with a halogen, like bromine gas, what am I going to get? Now, okay, I can tell you you're not going to get any, you're going to get nothing. Why are you going to get nothing? It's because you need to have the proper catalyst for you to get something. And it has to be specific. So specific that it has to be consistently with what's being reacted. So if you're going to do a bromination reaction with benzene, you better hope that you picked a catalyst that has bromine in it. If you decided to do this FeCl3, you're not going to get nothing. Nothing will happen. Okay? Now, the reason is very simple. It's because this catalyst actually takes part in the reaction. Now, I know, somebody probably told you before, I thought catalyst doesn't take part in the reaction. Well, yes and no. Catalysts do take part in the reaction. It's just that at the end of the reaction, you get the same thing back. This is never consumed. You're not going to walk out of this reaction without iron 3 bromide. But nobody said that this bromide right here, or any of these 3 bromide, is the same bromide that you came in with. Nobody said that. Okay? But what you're guaranteed is that at the end of this reaction, you'll still have this compound. Okay? Alright, let's continue on. It's actually a substitution reaction, okay, where any of these hydrogen can be substituted. Any of these guys can be substituted. I'm going to say this guy is going to get substituted. And what you're going to have here is a bromine plus HBr. Okay, so let's take a look at a simple mechanism here. So bromine will actually break apart, okay, to give you 2 bromine. And I guess what you can see is these two are going to come together to form HBr, leaving this carbon and this bromine all alone. And hey, bromine, come to us. Let's get together and form bromobenzene. Okay. Now, reaction number 2. This is where the fun begins. Let's use a different color. Let's start with what we just finish. Bromobenzene, right? What if I had decided to react this with more bromine gas? What will happen? Well, remember, always think outside the box. You will get this. Okay? You will have a substitution for this. Does it mean that's it? No, of course not. Because why can't I substitute this one? Why can't I substitute that one? Right? That can happen. So for this reaction, I don't always have to have ortho. I can have meta. Why not? If I can have meta, I can have para. Why not? Okay. Now, can I substitute this one? Yeah. But that's the same thing as this. Still a meta. Okay. So again, what makes organic chemistry hard is that it's not just as simple as this. I wish it was just as simple as this. But there's always cases where, hey, you know, this can happen too. Yeah, this can happen too. Okay. So under a reaction vessel, if you're reacting, you know, bromobenzene with bromine gas, potentially you can get 3 different products. Okay, or if there's a lot of these in excess, your reaction vessel will have a mixture of all 3 products. So 33.3% here, 33.3, 33.3. Okay, so hope you guys are comfortable with substitution. So let me just give you one to do. So I have a benzene with already existing bromine. Oh, let's not make, yeah. And I'm going to react this with chlorine gas. If I react this with chlorine gas, I better make sure my catalyst has some sort of chlorine in it. Now, you may be thinking, hey, earlier you used iron for the cation, now you use aluminum. Is it that specific? No, it's actually not that specific. You can use aluminum if you like. No big deal. Okay. Well, you can have this. Okay. You can have this, or you can have that. Okay. Are you comfortable with that, guys? All right. Let's clear the page. Let's take a look at the third reaction, number 3. This one has a name. It's a substitution reaction. So again, I have my benzene. I'm not going to put in the hydrogen. I'm banking on the fact that you know that there are hydrogens for each carbon, and I'm reacting this with hydrogen nitrate. Okay. The idea is very similar. You're under some sort of acidic condition, okay, a strong acidic condition like sulfuric acid. If that's the case, a nitro group, okay, will break apart from the hydrogen. So these two are going to break apart. You're going to get H plus and NO3 minus. Okay. And actually, you're gonna get actually OH and NO2 minus. Okay, that's what you're gonna get. NO2 plus, sorry. All right, so the NO2 will come attack one of the hydrogen, doesn't matter which hydrogen, to give you a nitrobenzene plus water. Okay, because the OH is going to take the H. Just draw the H right here, just so that you kind of know. Okay, so H2O comes over here, and NO2 go over there. Okay, just like what I just showed you. Anyway, that's substitution. So here's another type of substitution. I have a benzene reacting with an alkyl halide under acidic condition. Oh, sorry, not acid. This is not an acidic condition because it's not hydrogen nitride. It's a halide, so therefore it's a chlorine halide, so I have to make sure that the chlorine stays. Okay, the same idea as the halogenation we saw before, but the question is, what is the product that you're going to get? Now remember, these guys have H's. Okay, so what you're going to be seeing here is H taking Cl. Okay, it's going to take Cl. So the CH2CH3 will come and attack the carbon from the benzene. So at the end, you're going to get this. Okay. Anyway, hopefully you guys kind of get a hang of it. Okay, the reaction of benzene is really simple. This is really not too many because benzene is a very, very stable compound. So there's not a lot of reaction out there for benzene. So there's more, of course, but those are the three that you really need to know. All right, it's going to be a shorter day today, so let's call it. Tomorrow, we're going to look at reaction of alcohol. Now, that's going to be a big one because the reaction of alcohol will result in a new functional group called ether. So we'll get ready for that tomorrow. All right, bye now.